This video is to help you do prompts B1, B2, and prompt B3 in your Chapter 9 post-lab write-up. So for prompt B1, you're going to be asked to create your own DTNB extinction coefficient for your converting your DTNB absorbance values back to sulfhydryl groups. That's going to be in prompt B2, where you're going to take the absorbance values and then convert it to the micromoles of SH groups or sulfhydryl groups or cysteine groups that react with the DTNB molecule. And knowing the concentration and also the volume of your DTNB assay, you can then calculate the total nanomoles for your SH groups or cysteine residues that reacted with the DTNB in the first part of Chapter 9. Once you get this value for prompt B3, that's going to be the first half of the division that you have to do to find out the number of sulfhydryl groups per GAPDH molecule. So for prompt B1, just kind of like as an aside, we don't have a DTNB standard that we can use that we can measure at our benchtop spectrophotometers with our glass test tubes and measure at the Carry 60 UV visits with our UV cuvettes. We just don't have anything like that because of the way that DTNB works. DTNB only gives off a signal once it has reacted with a thiol group or a sulfhydryl group, and what we're going to do is just use NADH kind of like as a substitute for that. Remember that we measured DTNB absorption at 412 nanometers, but we're going to be using the values of NADH at 340 nanometers. But the concept is pretty much going to still be the same. And so what I'm going to use here is, I guess, Microsoft Paint to kind of go through these calculations. The concept is that the absorption that you have for the UV cuvettes, and again, this is just reviewing the basic concepts back in Chapter 3 when you had to do this for the LDH activity assays. The ratio of the absorbance that you get at the UV with a UV cuvette against the absorbance at the spec, which we'll call, apparent, is going to be equal to their corresponding, Beer's law formulas ratio as well. So that's also going to be the concentration times the path length times the, for the top part, it's going to be the UV extinction coefficient. And then also the ratio for the apparent is also going to be the concentration, its path length, and the extinction coefficient. Actually, I should not call this apparent. I should call this absorption here, the test tube or something like that, because it's not apparent just yet. And this extinction coefficient will also be the test tube as well. So for this formula, we can already have some variables cancel out because concentration is something that's intrinsic to the sample. In this ratio over on the right side, the concentrations are going to be the same, and so they'll actually cancel out. For the UV cuvette, because we do use this is going to be in per molar per centimeter, and the path length for our UV based measurements is 1 centimeter. This will also just pretty much cancel out here. The per centimeter for the extinction coefficient and also path length will disappear. And what we can do now here is kind of combine the extinction coefficient for the test tube for the DTNB and also its path length into one single extinction coefficient that we'll just call the apparent extinction coefficient. And that will not have a path length or a per path length unit associated to it. It's just going to be per molar. So we can pretty much figure this out now, what our apparent custom extinction coefficient is, because I provided UV absorbance values and also test tube absorbance values, and also I provided the DTNB UV extinction coefficient. So your Chapter 9 BTF data Excel file that I distributed on Blackboard is going to have those absorbance values at 340 nanometers right here. And so what I'm going to do now is basically finish off this part B1 calculation here by substituting in all the values that we know. So, and I'm actually, before we go ahead and even get started with this, I'm just going to rearrange all of these variables to the formula that we kind of are used to for how to calculate the apparent extinction coefficient. So what I'll do is I'll essentially cross multiply everything here. Remember that the only variables that we have left on this side is the UV extinction coefficient and also the apparent extinction coefficient here. So I'll just cross multiply everything here. And over on the left side, I'll have the apparent extinction coefficient multiplied by the UV absorbance value equals, and then the other cross multiplied product is going to be the UV extinction coefficient times the absorbance of the test tube. And then just to kind of finish this off here, I'll just divide both sides by the UV absorbance value. Wish there was a better way to do this than having to do it on Microsoft Paint, but whatever. And now what I'm just going to do is kind of discard everything up here. And this part will also disappear too. So now what we have here is, in order to calculate our apparent extinction coefficient, we need to multiply our UV extinction coefficient, which is 14,000 per molar, by our absorbance of NADH at the test tube divided by the absorbance of NADH at the UV cuvette. So that's going to basically now be, where do I go to write this? Okay, pen. The apparent extinction coefficient is equal to, and then I'll just go ahead and try to type this out now. 14,000 per molar times, and then the first part of the numerator is going to be the absorbance of the test tube, which we have over here is 0.607, or sorry, 0.605. Remember that absorbance is unitless, so that does not have a unit there. And then we're going to divide that by the UV absorbance of NADH at 340 nanometers, which is going to be 0.621. Oh, this little issue here. And then all we basically have to do now is just resolve this with a calculator. And I am going to take 14,000, multiply that by 0.605 and divide it by 0.621. And now my own custom apparent extinction coefficient for the remaining parts that I'm going to use for prompts B2 and B3 is, if I can show this, that is equal to 13,639 per molar. So that's the value that I'm going to use for solving now prompts B2 and B3. So what I want to do now is now go back to the post lab write-up. DTNB reactions 4 and 5 were performed to modify the cysteine residue in native and denatured states of GAPDH respectively. Because we want to calculate a total number of cysteine residues per GAPDH protein, we will use our DTNB measurements from reaction 5. Using that, the extinction coefficient that we solved previously and are converting our 60-minute time point for reaction 5, we want to go to micromoles of DTNB. All right, so the first thing that we need to do is set up Beer's law for this problem. So I'm going to create a new Microsoft Paint file here, just so I don't, erase any of my previous work. Beer's law tells us that the absorbance for any given sample is going to be equal to its concentration times its path length times the extinction coefficient for that. We don't have path length. Path length and the extinction coefficient of the test tube have been integrated into one entire unit called the apparent extinction coefficient. So that's essentially what we're going to use here for these calculations, is absorbance equals concentrations times apparent extinction coefficient. We know what the absorbance value is. The absorbance value is the 60-minute time point for reaction 5 for those DTNB assays, and that's going to be 0.480. That's for the TF data. Otherwise, use the last 60-minute time point that you have for your reaction 5 DTNB assays. So my absorbance is going to be 0.480, and that is equal to the concentration that we actually want to find out. And it's going to be, the prompt asks us to calculate that in micromolar. And our apparent extinction coefficient that we solved in the previous step is 13,639 per molar. So that is going to get multiplied by this extinction coefficient, the apparent extinction coefficient that we solved, 13,639. And units is very important here because it's going to determine what our concentration is afterwards. And here the units is per molar. So the only thing that we have to do now is resolve what this concentration is by dividing both sides by this apparent extinction coefficient value, 13,639 per molar. And do that to the left side as well. Wish I had like a stylus or something. It would have been nice to do this. And then we end up getting concentration is equal to, and we're going to resolve what this, what's it called? This calculation is here. So 0.480 divided by 13,639. And that is difficult to get everything on one page. 3.519 times 10 to the negative 5. And the units for this is going to be molar, because per molar is in the denominator. And if something's in the denominator with a, to the power of -1, essentially you can just flip that back up to the numerator with no exponent or anything like that. So pretty much we can just tack on the units molar here. But the prompt asks us to give this calculated value in per micromolar. Or sorry, not per micromolar, 2 micromolar. So we know that micromolar is times 10 to the -6. So if we have a molar here, we can just set up another conversion ladder here, put the denominator of 1 at the bottom, and then the next conversion sequence that we have in our conversion ladder is that for every 1 molar, that is the same as 10 to the 6 micromolar. Oh, God, these micros are so terrible. And when we resolve this, basically what we're going to do is now take that same value and multiply that by million. We get now 35.193 micromolar. And that is our answer for the prompt B2 exercise. Now, we're not just done yet for this calculation, because prompt B3 asks us to find out what the total nanomoles value is for the number of hydrogen groups in that reaction. So if we have concentration, in order to find nanomoles, we need to know what our volume is. And thankfully, we do know what our volume is for that, because we know that the whole DTNB reaction happened in a 3 mil reaction itself. So I'm going to set up another paint board here and just carry over the answer from the previous prompt. So 35.193, 35.193 micromolars. Remember that, you know, we're not going to be too much of a stickler for significant figures. I do have many, many digits from my previous answer, but I just pretty much only decided to carry over a few more decimals here. You can carry as many decimals as you want in your own calculations, but just please do not report so many decimal units for your actual answers for your post-lab write-up, because your absorbance values and your extinction coefficients don't have, you know, 10 or 20 decimal units to them. So if we know what our concentration of hydro groups, and we also know what our you know, DTNB volume is, we can actually figure out how many nanomoles of hydro groups there were in this DTNB reaction. So we have to do a little bit of conversion here. 35.193 micromolars. I'll just pretty much break up the micromolars units into the micromoles per liter. So that's going to be micromoles per liter. And here we have to do another conversion for the volume, because these don't match up. 3 mils is also the same as 0.003 liters. So now that we have our volumes matching and they'll cancel out, we can just go ahead and resolve this calculation by taking our previous answer, 35.193, and multiplying that by 0.003 liters. And now what we have here is 0, kind of put that there. We have 0.105579 micromoles. Remember, this was in micromoles because our first starting conversion was micromoles. But the post-lab write-up is asking us to report our answer in nanomoles. So we have to do another conversion here. We know that there are 1,000 micromoles for every nanomole, so we can just multiply our answer by 1,000. And our final answer should be 105.579 nanomoles. Again, we weren't this precise with our absorption values. So if our absorbance values had 4 digits there, 4 significant digits, or I guess it should actually be 3 significant digits, then we should report something as 106 or 105.6. Should actually just remove that decimal, nanomoles there. So that is going to be the answers for, or not the answers, the how to perform the work for prompts B1, B2, and B3 in the Chapter 9 post-lab write-up. Once you get your answer for prompt B3, then essentially that is going to be the numerator for what you have to calculate for prompt B9, since doing this requires your answer from prompt B3. And the rest for prompts B4 through 8 is going to be in a separate video tutorial on how to do that.